So there are also three laws, they're called the integrated rate laws. And the reason they're called the integrated rate laws is because calculus has been applied to these. So they've undergone the process of integration, which you don't really need to know anything about. You just need to be able to tell which is the zero order reaction equation, which is the first order equation, and which is the second order equation. Just like when we were plotting straight lines, when you plot the concentration, that is indicative that it's a zero order process. If you're plotting the natural log and it makes a straight line, that's indicative of a first order process. And if you're plotting the reciprocal and it's a straight line, that's indicative of a second order process. So these equations really aren't any different from one another. It's just the first one uses concentrations because that's where the linear relationship lies. The second one uses natural logs, and the third uses reciprocals. If you were to look at each of these, the first piece is always the concentration of A with the subscript of a T. That just means the concentration at a given time. The concentration of A at a given time. And that just means however far into the reaction you've progressed. If you've progressed 10 seconds, then this would be the concentration at 10 seconds. This would be the natural log of the concentration at 10 seconds. And this would be the reciprocal of the concentration at 10 seconds of A. The step here has A with the subscript of 0, or ln of A with the subscript of 0, or the reciprocal of A with the subscript of 0. This is just your initial concentration of A. The reason it's a 0 is because it's at time 0, and at time 0 is the beginning of the reaction. So you can simply plug in your initial concentrations of A here, there, or there, depending on whether you're 0, first, or second order with respect to A. On the right side of the equal sign, you have negative K, which is just your rate constant. And then each of them also has T, which is simply the time that has elapsed. What these reactions allow you to do is solve for a missing variable. For example, if you knew that a reaction was 0 order with respect to A, you could deduce the ending concentration of A by subtracting the initial concentration of A, set equal to the negative of the rate constant times however many seconds have passed. If you know 3 of these 4 variables, you can solve for the 4th one, as long as you know whether it's 0, first, or second order with respect to A. These really are powerful equations because frequently you don't know what the concentration should be at a certain time, but as long as you know K, how much time has elapsed, and how much you had to begin with, you can work backwards to solve for these unknowns here. Or if you know the initial concentration, you know your final concentration, and you know the time that elapsed, you can pretty readily solve for K using either of these. The only issue here is you must know whether it's 0, first, or second order with respect to A, and make sure that you use the appropriate integrated rate law.